In this video, we're going to focus on the second law of thermodynamics. We're going to talk about how to solve problems associated with heat engines, efficiency, the Carnot engine, and refrigerators as well. So let's begin. Now we know the first law is basically a statement of the conservation of energy. The change in the internal energy is equal to Q minus W. So let's say if this box represents the system, and if we add 300 joules of energy, that's Q, that's the heat energy absorbed by the system, and let's say the system performs 100 joules of work. So it expends 100 joules of energy. So the system gained 300 joules of energy, it lost 100, so the change in the internal energy is a gain of 200. So energy is conserved. That's the main idea behind the first law of thermodynamics. The main idea behind the second law of thermodynamics is that irreversible processes tend to increase the disorder of a system. But let's talk about reversible and irreversible processes first. Let's say if you have a ball placed above ground level. This ball naturally will fall down to the ground. The ball is not going to go up by itself from the ground. That just doesn't happen. So this is an irreversible process. The ball will naturally fall from a high position to a low position. It doesn't naturally go from a low position to a high position. The first process is a spontaneous process. It happens naturally without any assistance. The second process is non-spontaneous. It doesn't happen on its own. The only way to make it happen is to put energy into the system to lift the ball to a high position. Now, what about a reversible process? Let's say if we have a level surface and if we have a ball. The ball can easily roll towards the right just as easily as it can roll towards the left. It can go in either direction because the surface is leveled. So this is an idea of a reversible process. It can occur in both directions. Now, and let's not take friction into account. Now let's talk about heat. Let's say if we have a high temperature reservoir and a low temperature reservoir. So let's say over here it's at 600 Kelvin and the temperature on this side is 300 Kelvin. Heat naturally flows from hot to cold. It flows from a high temperature to a low temperature. So in that direction, it's spontaneous. Heat just doesn't flow from a low temperature to a high temperature. It doesn't happen. So the direction towards the right represents a spontaneous process. And going back in the other direction is a non-spontaneous process. So you don't need anything, you don't have to do anything in order to get heat to flow from hot to cold. It's going to happen naturally. However, if you want to cause heat to flow from, let's say, a cold object to a hot object, since it doesn't happen naturally, you have to put in energy into the system to pump heat from a low temperature environment to a hot temperature environment. Just the same way as you got to put energy to lift the ball from ground level to a higher position. It takes energy to do that. So basically, this is one statement of the second law of thermodynamics. Heat always flows from hot to cold and never flows in reverse. Now let's say if the temperatures were approximately equal. So in the last example, where the temperatures were 600 and 300 Kelvin, that's an irreversible process. Heat flows in one direction on its own. It doesn't flow in the other direction. But let's say if the temperatures are approximately the same. If they're both 300 Kelvin, then equilibrium will be established. The amount of heat that flows towards the left is equal to the rate of heat that flows towards the right. And so this is a reversible process. an equilibrium is established in this case. When you have an irreversible process, like the one we had in the last example, the entropy, or the disorder, tends to increase for an irreversible process. Things happen in such a way that the disorder goes up. For example, think of your room. It's easier for your room to become messy than it is to keep it clean. Typically, you may find that your room naturally becomes disorderly, but it takes effort, it takes work to put it back in order. So for most natural processes, for irreversible natural processes, the entropy tends to increase, or the disorder. Now for reversible processes, the total entropy can increase, or if you have an isolated system, at best it can remain constant. The change in entropy could be zero. But natural processes tend to lead towards disorder, and that's another idea of the second law of thermodynamics. Now let's move on to heat engines. So what exactly is a heat engine? A heat engine is basically a device that converts heat energy into mechanical energy or work. So let's say if we have a hot temperature reservoir. Let's say this is at 500 Kelvin. And if we have a low temperature reservoir, which is at 300 Kelvin. And let's say this big box in the middle is the system. Heat will naturally flow from hot to cold. So the amount of heat energy that flows into the system, or that is absorbed by the system, is known as QH. Now, the amount of heat energy expelled by the system into the environment or into the low temperature reservoir is QC. Now, as heat flows from hot to cold, the system can absorb some of that heat energy and use it to convert it to mechanical work. So that's a heat engine. Now, the heat engine is not able to take all of the heat energy that it absorbs and convert it to work. It takes a fraction of that energy. Most of the energy is expelled into the environment, but the heat engine takes some of it and converts it to mechanical work. The work is equal to the difference between QH and QL. QH tends to be positive because anytime the system absorbs heat energy, Q is positive. QC tends to be negative because heat energy is released by the system. So that's why we have the absolute values. Now the efficiency is equal to the work divided by QH times 100%. And sometimes you may need to use power. Power is equal to work divided by time. And work is power multiplied by time. Keep in mind the unit of power is the watt. 1 watt is 1 joule per second. So power is the rate of energy transfer. So if you have, let's say, 70 watts, that means that in 1 second, 70 joules of energy is being transferred every second. Now let's work on some problems. A heat engine absorbs 2,500 joules of heat and discards 2,100 joules of heat. Calculate the work performed by this engine and its thermal efficiency. So let's say this box represents the system. Now, 25 joules of heat energy enters the system. So this is QH. And 21 joules of heat energy leaves the system. So this is QC. What is the work output of this system? The work is basically the difference in these two values. If 25 joules of energy enters the system, for it to maintain its state, 25 joules of energy must leave the system. Otherwise, the temperature of the system will keep on going, and that could be damaging. So the work is going to be the difference between QH and QC. In this case, it's going to be 400 joules. It's 2500 minus 2100. Now, what about the efficiency of this engine? The efficiency is basically the work divided by QH times 100%. So it's going to be 400 divided by 2500 times 100%. Now, 400 divided by 2500 is 0.16 times 100. So this device is 16% efficient. So what that means is that 16% of the heat energy that travels through the system is converted to mechanical energy. The other 84% is expelled to the environment. So 16% travels this way, and the other 84% escapes to the environment. A jet engine releases 5,000 joules of energy per cycle and performs 800 joules of work. How much heat is absorbed by this engine per cycle? So let's say this is the system, and it releases 5,000 joules of energy. So this is equal to QC. And the work output is 800 joules per cycle. So how much heat energy is absorbed by the system? QH is equal to W plus QC. And of course, we're dealing with absolute values. So if a total of 5,800 joules leaves the system per cycle, then that same amount of energy must enter the cycle. So that's QH, 5,800 joules. So that's how much heat energy is absorbed by the system per cycle. Now what about B? What is the thermal efficiency? The thermal efficiency is going to be the work performed by the machine per cycle divided by QH, the heat energy absorbed by it, times 100%. And this is about 13.8% efficient. So how much work can this engine perform in 50 cycles? How would you answer part C? The answer to this is straightforward. If 800 joules of energy is produced per cycle, then we simply need to multiply by 50 cycles. Notice that the unit cycles will cancel, and this will give us the work output during those 50 cycles. 8 times 5 is 40. And then after that, we simply need to add the 3 zeros. So 40,000 joules of work can be performed by this engine in 50 cycles. Now what about part D? If the engine completes each cycle in 0.20 seconds, what is the power rating of the engine? Now we know power is the ratio of work and time. So in one cycle, the engine performs 800 joules of work. And one cycle occurs in 0.20 seconds. So we simply need to divide the two. 800 divided by 0.20 is about 4,000 joules per second. So in 1 second, this engine generates 4,000 joules of work. In 10 seconds, that would be 40,000 joules of work. So you could say it's 4,000 joules per second, or simply 4,000 watts. A 1,000 joules of heat energy is absorbed per cycle by a diesel engine that is 15% efficient. How much work does it perform per cycle? Well, let's find out. So here's our system, and 8,000 joules of energy enters into it per cycle. To calculate the amount of work performed, we need to realize that 15% of the energy travels this way, and the other 85% is expelled to the environment. So what is 15% of 8,000? All you need to do is multiply 8,000 by 0.15. To convert 15% into a decimal, divide it by 100, or simply move the decimal point 2 units to the left. So 8,000 times 0.15 is 1,200 joules. So that's the output work. Now, if you take 8,000 and multiply it by 0.85, that's going to give you the output work, which is 6,800. And you can check your work. As you can see, these two numbers add up to 8,000. So anytime you want to find the work from QH, use this equation. W is equal to the efficiency times QH divided by 100. And if you want to find QC, you can take 8,000 subtracted by 1,200, and that will give you QC, 6,800. Or you can multiply it by 85%. Both ways work. An engine has a heat input of 175 kilowatts and a work output of 21 kilowatts. What is the thermal efficiency? So the thermal efficiency is the work divided by QH. Now, this equation will work if you have the units of joules or if you have units of power such as watts. So the work output is 21 kilowatts and QH is 175 kilowatts times 100%. So the thermal efficiency in this problem is simply 12%. Now, how much heat energy? Well, I'm jumping to part C. Part B. At what rate is heat discarded into the environment? So we have 175 kilowatts of power being absorbed by the system. 21 kilowatts is released, it's converted to mechanical work. So the difference between these two, 175 minus 21, represents the amount of heat or the rate of heat energy that it leaves into the environment. So the answer is simply 154. Now part C, how much heat energy is released into the environment if this machine were to operate continuously for 1 day? So QC divided by time is basically 154 kilowatts, which is 154 kilojoules per second. So we need to find out how many seconds are there in 1 day, and then we can calculate the total amount of heat energy released into the environment. So in 1 day, there's 24 hours per day, and there's 60 minutes in a single hour, and there's 60 seconds in a single minute, and 154 kilojoules of energy is released every second. So it's 24 times 60 times 60 times 154. So it's 13 million joules of energy. A gasoline engine takes in 12,000 joules of heat energy per cycle and produces 2,400 joules of mechanical work. So let's begin by drawing a picture. So 12,000 joules of heat energy enters the system, and only 24 joules of mechanical work leave the system. So therefore, QC is the difference between these two. 12,000 minus 2,400 is about 9,600 joules. So that's the answer to part A. Now what about part B? What is the thermal efficiency of this particular engine? Well, we know that efficiency is the work divided by QH times 100%. So W is 2,400, QH is 12,000, and so this machine is about 20% efficient. Now part C, what mass of fuel is consumed in each cycle if the heat of combustion is 45,000 joules per gram? So what we need to use is QH, because the energy absorbed by the system comes directly from the gasoline. So let's start with 12,000 joules, and let's convert it to grams. So this number tells us that 1 gram of gasoline releases 45,000 joules. And you want to write it in such a way that the unit joules cancel. So you get grams. So this is going to be equal to 0.2667 grams. Now what about part D? If the engine goes through 50 cycles per second, what is the power rating in watts, kilowatts, and horsepower? Power is equal to the work divided by the time. And we have the mechanical work. It's 2,400 joules per cycle. So what we need to find is the time it takes to complete one cycle. Now we're given 50 cycles per second. That's the frequency, which is the same as 50 hertz. The period represents the time it takes to complete a single cycle, and it's 1 divided by the frequency, or 1 over 50. So in 1 second, 50 cycles will be completed. So if we take 1 and divide it by 50, this will give us 0.02, which is 0.02 seconds per cycle. So in 0.02 seconds, this device will generate 2,400 joules of mechanical work. So if it can perform 2,400 joules of mechanical work in 0.02 seconds, then its power rating is 120,000 watts. Now how much is that in kilowatts? Well, let's convert it. 1 kilowatt is equal to 1,000 watts. So 120,000 divided by 1,000 is 120 kilowatts. Now what is the answer in horsepower? Well, you need to know the conversion. 1 horsepower is equal to 746 watts. So if you take 120,000 and divide it by that number, you're going to get 160.9 horsepower. Now let's talk about the Carnot cycle. The Carnot engine is basically the ideal model of a heat engine. It was designed to represent or to obtain the maximum possible efficiency. So it's simply an ideal model. No other engine can have an efficiency that's greater than the Carnot engine, at least as far as we know. But let's draw a PV diagram for this. So we're going to start at position A. In the first step of the Carnot cycle, we have an isothermal expansion. So going from A to B. During this isothermal expansion, heat is added to the system. So we'll call this QH. and the machine or the engine performs positive work. Anytime a gas expands, the work done by the gas is positive. Now in the second step, going from B to C, we have an adiabatic expansion. And during an adiabatic process, no heat transfer occurs, so Q is 0. However, since the gas is still expanding, the engine performs positive work during this process. Now, going from C to D, this process is known as an isothermal compression. For any isothermal event, the change in temperature is equal to 0. But going from C to D, heat is released from the engine into the environment. And because the gas is being compressed, the engine performs negative work, which means that the surroundings do work on the engine, so W is negative during this point. It takes effort to compress the gas. You got to put energy into it. And going from D back to A to complete the cycle, that is an adiabatic compression. Q is 0, there's no heat transfer, and because the gas is being compressed, the work performed on it is negative. So that's the Carnot cycle. But there's two equations that you really need to know for this ideal engine. The efficiency of the Carnot engine is 1 minus Tc divided by Th, where Tc is the temperature of the cold reservoir and Th is the temperature of the hot reservoir. And also, the ratio of Qc and Qh is equal to the ratio of Tc and Th. A Carnot engine takes in 4,500 joules of heat energy from a reservoir at 800 Kelvin. How much heat energy will be released to a cold reservoir at 300 Kelvin? So we can use this equation. Qc divided by Qh is equal to Tc over Th. So the absolute value of Qc, we're looking for that. And Qh is 4,500 joules. That's the amount of heat energy that is absorbed by the system, which comes from the hot reservoir. And Tc, that's the low temperature, or the temperature of the cold reservoir, that's 300 Kelvin. Th is the temperature of the hot reservoir, that's 800 Kelvin. So if we cross multiply, this is going to be 4,500 times 300, and that equals 800 times Qc. 4,500 times 300 is 1.35 million, and if you divide that by 800, you'll see that Qc is about 1687.5 joules. So now let's draw a picture. So let's say this is the system. 4,500 joules of energy enters the system, and 1687.5 joules leaves the system. So the temperature of the hot reservoir is 800 Kelvin, and the temperature of the low or the cold reservoir is 300 Kelvin. Now once we have QH and QC, we can calculate the work, which is the difference between the two values. It's QH minus QC. So this engine performs 2,812.5 joules of work. So now we can calculate the efficiency. So one way we can do that is using QH over W, and that's going to be, I wrote it the other way. It's supposed to be W over QH times 100%. So 2812.5 divided by 4500 times 100 is about 62.5% efficient. Now you can also get that same answer using another equation if you're dealing with a Carnot engine. So we can use this equation to get the answer. So it's 1 minus Tc divided by Th. So this gives you a decimal answer, 0.625. And if you multiply that by 100, it represents 62.5%. A heat engine absorbs 4,000 joules of energy from a hot reservoir at 500 Kelvin and ejects 3,000 joules of heat energy from a cold reservoir at 300 Kelvin. So let's say this is the hot reservoir, and it's going to put in 4,000 joules of energy into the system, and 3,000 joules of heat energy gets ejected to a cold reservoir at 300 Kelvin. So how much work is performed by the engine? We know work is QH minus QC, so 4,000 minus 3,000. The work performed is simply 1,000. Now what about B? What is the efficiency of this engine? The efficiency is simply the work divided by QH times 100%. So that's 1,000 divided by 4,000, which is 0.25, times 100. That should be 25%. So that's the efficiency of the actual heat engine. Now what is the maximum theoretical efficiency? So we need to find the efficiency of the Carnot engine. So we're going to use the equation 1 minus Tc over Th. So that's 1 minus 300 over 500. And that's going to be 0.4. So if we multiply that by 100%, the maximum efficiency of this engine is 40%. That's as high as it can go. So 25 divided by 40 is 0.625. So this engine is operating at 62.5% of its Carnot capacity, or its Carnot efficiency. Now let's talk about refrigerators and air conditioners. These devices work in the opposite direction compared to a heat engine. In a typical heat engine, heat flows from a hot reservoir to a cold reservoir. Let's say this box is the system. So heat flows from hot to cold. As that happens, the heat engine can perform work. So a heat engine converts heat into mechanical work, but a refrigerator does the opposite. In a refrigerator, electricity is used to perform work on a device and to pump heat from a cold reservoir to a hot reservoir. So this is QH and this is QC. Now, just like the previous equations for refrigerators, air conditioners, and heat pumps, the work is still the difference between QH and QL. And QH is still the sum of QC and the work. The only difference is you're using work to pump heat from a cold environment to a hot environment. So how can we compare two refrigerators and know which one is more efficient? Is there a system in which we can measure the performance of a refrigerator? There's something called the coefficient of performance. Some books might use the symbol K, others might use CP. But for a refrigerator, it's the ratio of QC and the work that you put into it to pump heat from the cold environment to the hot environment. The purpose of a refrigerator is to cool something down. And so the more heat that you can take away from the cold reservoir, the more efficient the refrigerator is. So it's defined as QC over W. Now for a heat pump, the coefficient of performance is defined differently. Let's say if you have a house and you're up north and it's very cold outside, it's winter, and you want to use a heat pump to pump heat into your house to keep it warm. You're concerned with QH rather than QC. You want to know how much heat is being delivered into the house as opposed to just how much heat is being absorbed from the cold reservoir. So for a heat pump, the coefficient of performance is measured differently. What matters is how much heat is coming into the house rather than how much heat is being removed from a cold reservoir, which is important for a refrigerator or an AC unit. So the equations are defined differently for these different devices. So just keep that in mind. Now, for a refrigerator, to calculate the Carnot coefficient of performance, this is the maximum ideal that you can get to. It's equal to TC divided by TH minus TC. So that's another equation that you want to have with you. A refrigerator uses 1200 joules of work to pump 3000 joules of heat from a cold reservoir at 275 Kelvin to a hot reservoir at 320 Kelvin. What is the coefficient of performance? So for a refrigerator, the coefficient of performance is equal to QC divided by W. QC, that's the amount of heat that is pumped from the cold reservoir, which is 3000 joules. And the amount of work that is used to accomplish that is 1200 joules. So we simply have to divide these two numbers. So the coefficient of performance is 2.5. Now, what is the maximum coefficient of performance? So basically, what is the coefficient of performance for the Carnot device? The equation is equal to TC divided by TH minus TC. So TC, the temperature of the cold reservoir, is 275 Kelvin. The temperature of the hot reservoir is 320 Kelvin minus the 275. And if you type this in, you should get an efficiency, or rather a performance of 6.1. So that's the maximum coefficient of performance for this particular device. But the actual performance is 2.5. Now, how much heat is delivered to the hot reservoir? So let's draw a picture. So we're putting in 1200 joules of work, and at the same time, let's say this is the cold reservoir at 275 Kelvin. We're pumping 3000 joules of heat energy from the cold reservoir into the hot reservoir. QH is basically the sum of W and QC. So all we need to do is add 1200 and 3000. So about 4200 joules of energy is being pumped into the high temperature reservoir. And so this is the answer for part C. A Cardinal Freezer removes 1500 joules of heat energy from a reservoir at 250 Kelvin and pumps it to a reservoir at 320 Kelvin. How much heat energy is transferred to the hot reservoir? Well, since we have a Carnot device, we can use this equation. QC divided by QH is equal to TC divided by TH. So we have the value for QC. That's the amount of heat energy being released from the cold reservoir at 250 Kelvin. So QC is 1500. TC is 250 Kelvin. And TH, that's the temperature of the hot reservoir, that's at 320 Kelvin. So let's go ahead and calculate QH. So let's cross multiply. So it's 250 times QH, and that equals 1500 times 320. 1500 times 320 is 480,000, and if we divide that by 250, we'll see that QH is 1920. Now that we have QH, we can calculate W, which is the difference between QH and QC. So 1920 minus 1500, it's 420. So let's draw a picture. So we're putting in 420 joules of work in each cycle, and we're pumping 1500 joules of heat energy from the cold reservoir. And so 1920 joules of heat energy is going to be transferred to the hot temperature reservoir. And so this is the answer for part A. Now what about part B? What is the coefficient of performance for this device? The coefficient of performance for a refrigerator or even a freezer is going to be QC divided by W. QC is 1500 and W is 420. So the answer is about 3.57. Now we can also calculate K using the other equation, since this is a Carnot device. So let's use this, TC divided by TH minus TC. So TC is 250, TH is 320, and 320 minus 250 is 70. 250 divided by 70 gives us the same answer of 3.57. A heat pump uses 2500 joules of work to transfer heat energy. How much heat energy is absorbed by the hot reservoir? So for a heat pump, K is equal to QH divided by W. So to find QH, it's going to be K times W. So it's going to be 3.0 times 2500, which is 7,500 joules. Now once we have that, we could find QC, the amount of heat energy released by the cold reservoir. So let's draw a picture. So 2500 joules of work is being put into the system, and 7,500 joules, 3 times the value of W, is being transferred to the hot reservoir. So how much energy is being pulled from the cold reservoir? Well, it has to be the difference between these two numbers. 7,500 divided by or minus 2,500 is 5,000 joules. So that's the answer to part B. And that is it for this question. As you can see, these problems are not too difficult. You can solve them. As long as you know the equations and understand how it works, you can find whatever you need to look for. Now, going back to heat engines, I want to talk about the Otto cycle. If you haven't learned this in class, feel free to skip over it. But let's draw the PV diagram. So we're going to start at position A. In the first step, we're going to have an adiabatic compression. So we're going to go from A to B. Now during this adiabatic compression, the volume decreases greatly. We have volume on the x-axis, pressure on the y-axis. As we decrease the volume adiabatically, the pressure is going to go up and the temperature will increase as well. These conditions make it favorable to ignite an air-fuel mixture. The Otto cycle is the ideal model of a gasoline engine. And so when you compress the air and the fuel together, and as you increase the pressure, you increase the collisions, and as you increase the temperature, you increase the energy of the molecules, thus causing increase in the rate of reaction between the air and the fuel, which will make it favorable to ignite. Now during this adiabatic compression, Q is 0. No heat is transferred. And in order to compress something, you have to perform work on the gas. You have to apply a force to compress it. So the work done by the gas is negative because the surroundings is doing work on the gas. So you have to put in energy during this process. Now in the second step, we have an isochoric process. We're going to go from B to C. Now during an isochoric process, the change in volume is 0. The volume is constant. This is also known as an isovolumetric process. Now in order for the pressure to increase, we need to increase the temperature, and the pressure will go up. And the only way to increase the temperature is to add heat. So during this part, heat is added in the cycle. So let's call it QH. So where does the heat come from? Well, in the first step, from A to B, during the adiabatic compression, once the air and the fuel ignites, that reaction releases a lot of energy. And so that energy basically is going to be used to heat up the surrounding gas, increasing the temperature and increasing the pressure as well. Now once we reach this state of high temperature and pressure, the next step is an adiabatic expansion. Let me draw that better. So C to D. Now during this adiabatic expansion, Q is 0. But anytime a gas expands, it performs positive work. Most of the work produced by the gas, actually all of it in this case, is from C to D. So energy leaves the system as mechanical work. Now what about the last part? That is D to A. So D to A is an isochoric process. The change in volume is 0. For any isochoric process, W is 0. Now notice that we're going down in the PV diagram. The pressure is decreasing, which means that the temperature must be decreasing as well. So that tells us that heat is being released from the system in order for the temperature to decrease. So this is QC during the Otto cycle. Now there's another equation that you need to know for the Otto cycle. The efficiency is equal to 1 minus 1 divided by R raised to the gamma minus 1. R is the compression ratio, and this symbol is the gamma ratio, which is Cp over Cv. So sometimes you might have questions relating to this equation. So I'll give you a few examples on that. What is the efficiency of an Otto cycle that has a compression ratio of 8.5 and a gamma ratio of 1.41? So using the equation E is equal to 1 minus 1 over R, gamma minus 1. This is going to be 1 minus, R is 8.5, gamma is 1.41, and 1.41 minus 1 is 0.41. 8.5 raised to the 0.41 power is about 2.4047. So the final answer is about 0.584, which represents 58.4%. What is the compression ratio of an Otto cycle that has an efficiency of 46% and a gamma ratio of 1.4? So let's rearrange the equation to solve for R. So the first thing we want to do is add this to both sides. It's negative on the right side, so if we move it to the left, it's going to be positive. And E is positive on the left side. If we move it to the right, it's going to be negative. So we can rearrange the expression and write like this: 1 over R raised to the gamma minus 1 is equal to 1 minus E, which is the same as 1 minus E over 1. Now what we're going to do is flip both fractions. So R raised to the gamma minus 1 is equal to 1 over 1 minus E. Now to get R by itself, we need to get rid of this exponent. The only way to do that is to raise both sides to the reciprocal of gamma minus 1, which is 1 over gamma minus 1. So 1 over gamma minus 1 times gamma minus 1, those two will cancel. And so we have this equation: R is equal to 1 divided by 1 minus E raised to the 1 over gamma minus 1. So now that we have the equation for R, let's go ahead and find it. So the efficiency is 46%. If we divide it by 100, it's 0.46 as a decimal. And gamma is 1.4. So let's take this one step at a time. 1 minus 0.46 is 0.54. And 1.4 minus 1 is 0.4. Now, 1 divided by 0.54 is 1.8519. And 1 divided by 0.4 is about 2.5. So the final answer is about 4.67. So that's the compression ratio for this particular Otto cycle. An Otto cycle has a maximum efficiency of 71% and a compression ratio of 8.9. What is the gamma ratio of the working substance? So what exactly is the working substance? Well, the working substance is the gas or fluid that is in the device. So let's say if you have a steam engine, the working substance is steam. Now let's start with the original equation. E, the maximum efficiency, is equal to 1 minus 1 over R, gamma minus 1. So just like we did before, we're going to take this term, which is negative on the right side. Let's move it to the left so it's positive. And then we're going to take E, which is positive on the left, move it to the right, and so it's going to be negative. So 1 over R, gamma minus 1 is equal to 1 minus E. And we're going to flip both sides just like we did last time. But this time, because we want to solve for gamma, we're going to take the natural log of both sides of the equation. Now, a property of natural logs allows us to take the exponent and move it to the front. So gamma minus 1 times the natural log of R is equal to the natural log of 1 over 1 minus E. So now we can divide by ln R. So gamma minus 1 is equal to ln 1 over 1 minus E divided by ln R. And then the last thing we need to do is add 1 to both sides. So here's the equation that we need. So E is going to be 0.71 and R is 8.9. So 1 minus 0.71 is 0.29, and natural log of 1 divided by 0.29 is about 1.23787. The natural log of 8.9 is about 2.18605. So the final answer is going to be about 1.566. So that's how you can find the gamma ratio if you're given the maximum efficiency and the compression ratio. Now let's talk about entropy. Entropy is a measure of disorder, and it's represented by the symbol S. Whenever a gas expands, whenever it increases its volume, the entropy of a system increases. Entropy is higher for gases than it is for liquids and solids, because gases, they have more random motion, they're more chaotic and disorderly, so they have a higher entropy value. Whenever you increase the temperature of a gas, you increase the kinetic energy of the molecules, and they're moving faster in a more random motion, so the entropy goes up with temperature. The change in entropy is the difference between the entropy of the final state and the entropy of the initial state. You can also calculate the change in entropy using this equation. It's equal to Q divided by T, where Q is the heat transferred into or out of the system. Now, this equation applies for a reversible isothermal process. Now, keep in mind, whenever you have an isothermal process, the change in temperature is zero. So there's only one single constant temperature for an isothermal process. Therefore, this equation applies in that instance. Calculate the change in entropy that occurs when 7 kilograms of ice melts at 0 degrees Celsius. And we're given the latent heat of fusion for ice. So delta S, is it positive or is it negative? What would you say? In order to melt ice, we need to add heat to it. Typically, when you add heat to something, the entropy usually increases. So delta S is positive in this case. Now, this is an isothermal process. When ice melts, the temperature remains constant until all of the ice cubes have melted into liquid water. So therefore, the change in temperature is zero. Whenever the temperature is constant, you can calculate delta S using this equation. It's simply Q divided by T, and Q is equal to M times L. It's the mass times the latent heat of fusion. So Q is equal to 7 kilograms times 3.34 times 10 to the 5 joules per kilogram. So as you can see, the unit kilograms will cancel. And then we're going to take that result divided by T, which is 0 degrees Celsius, but in Kelvin, that's 273 Kelvin. So if we multiply 7 times 3.34 times 10 to the 5, you should get 2,338,000 joules. And then we'll divide that by 273. So in this case, the change in entropy is 8,564 joules per Kelvin. So what can we do if the temperature is not constant? What if the temperature changes? How can we estimate or calculate the change in entropy? We're going to do it two ways. We're going to use a simple method to ballpark the answer, and we're going to use calculus to get the exact answer. So first, let's estimate the answer. You can still use the equation delta S is equal to Q divided by T, but you need to use the average temperature in Kelvin, not in Celsius. So first, let's calculate Q. We can use the equation Q is equal to MCAT since we have a temperature change. In the last problem, we had a phase change. When ice melts into liquid water, the temperature is not changing, so you want to use Q equals ML. But in this problem, the temperature is changing, so you want to use Q equals MC delta T. The mass is 4 kilograms. The specific heat capacity is 4,184 joules per kilogram per Celsius. Delta T, the change in temperature, could be in Celsius or Kelvin. The difference will still be 100. So as you can see, the unit Celsius will cancel, and kilograms cancels as well. So we're going to get Q in joules. So 4 times 4184 times 100 gives us a Q value of 1,673,600 joules. Now let's divide that by the average temperature. The average Celsius temperature between 0 and 100 is 50 Celsius. To convert that to Kelvin, add 273 to 50, which gives you 323 Kelvin. So now let's divide these two numbers. So the change in entropy is approximately equal to 5,181 joules per Kelvin. So let's round that to 5,200 joules per Kelvin. Now let's find the exact answer. Delta S is equal to the integral from A to B, or the initial temperature to the final temperature, of dQ divided by T. So that's the equation that you need. Now we know that Q is equal to MCAT. So we could say that dQ, which is the differential of Q, is equal to MC, which are constants, times the differential of T. That is the differential of the temperature. So let's replace dQ with MC dt. M and C are constants, so let's move that in front of the integral symbol. The antiderivative of 1 over x is ln x. Therefore, the antiderivative of 1 over t must be ln t. So this is mc, natural log of t, evaluated from t initial to t final. So final minus initial, if we plug in those two values, it's going to be mc, natural log t final, minus mc, natural log t initial. A property of natural logs allows us to condense two logs into a single log. So ln A minus ln B is the same as ln A over B. So knowing that, this expression is now equivalent to mc ln t final divided by t initial. This is the equation that you want to use to calculate the change in entropy whenever you have a temperature change due to heating or cooling an object. So let's go ahead and use that. So delta S is going to be the mass, which is 4 kilograms, times the specific heat capacity of 4184, times the natural log of the final temperature, which has to be in Kelvin. Keep in mind, delta T could be in Celsius or Kelvin, but if you see T without the triangle, it has to be in Kelvin. 100 plus 273 is 373. That's the final temperature. The initial temperature, which is 0 Celsius, is the same as 273 Kelvin. So it's 4 times 4184 times natural log 373 divided by 273. And this is equal to 5,223 joules per Kelvin. The other answer was like 5,181 joules per Kelvin. As you can see, if you round both of them, they're approximately equal to 5,200 joules per Kelvin. But this is the exact answer. This is the more accurate answer. The other one is simply an approximation. So this is the equation that you want to write down if you need to get the exact answer. 2 moles of an ideal monatomic gas expands adiabatically from 300 Kelvin to 250 Kelvin. The molar heat capacity of this gas is that number. Find the change in entropy. Now, whenever a gas expands adiabatically, the volume increases greatly, and it increases at a factor that's greater than the decrease in pressure. It turns out that adiabatic expansion cools the gas. The temperature goes down as well. Now, how can we calculate the change in entropy? Can we use this equation? And if we can, what is Q? Now, typically, you might be thinking Q equals MCAT, or some variation of this equation. Q equals NC times delta T, if you have the molar heat capacity. You can find Q that way. But it turns out that Q is equal to 0 for an adiabatic expansion or compression by definition. Whenever you have an adiabatic process, there's no exchange of heat. Heat is not absorbed by the gas or released by the gas. So this equation really doesn't apply. And because Q is 0 for an adiabatic process, the change in entropy is therefore 0. So watch out for this question. Let's try this problem. A Carnot engine absorbs 4,000 joules of heat energy from a hot reservoir at 800 Kelvin. How much heat energy does it release into the cold reservoir at 300 Kelvin? So for Carnot engines, you can use this equation. QC divided by QH is equal to TC over TH. So QC, we're looking for that. QH is 4,000. That's how much energy it absorbs from the hot reservoir. TC is 300 Kelvin, and TH is 800 Kelvin. So to find QC, if we cross multiply, it's going to be 4,000 times 300 divided by 800. So QC is 1,500 joules. So let's say this is the engine. Here is the hot reservoir, and here's the cold reservoir. So the engine absorbs 4,000 joules from the hot reservoir. And then it releases 1,500 joules into the cold reservoir. And this happens all within one cycle. So with this information, how can we calculate the net change in entropy of the engine? So let's find out the entropy change when the engine absorbs energy from the hot reservoir. It's going to be Q divided by T. And the temperature at the hot reservoir is constant. It's 800. So you need to use like the natural log function in this case. So Q is going to be 4,000 divided by 800. So delta S is positive 5 joules per Kelvin. Now what about the change in entropy of the engine when it releases energy into the cold reservoir? Because it releases energy, Q is going to be negative 1,500 and not positive. And the temperature is 300 Kelvin. So negative 1,500 divided by 300 is negative 5 joules per Kelvin. Now the net entropy change is the sum of these two individual entropy changes that occurs at the cold and hot reservoir for the engine. So it's going to be positive 5 plus negative 5, which is 0. So what does this all mean? For any cyclic reversible process, the change in entropy will always be 0. Because if you start from position A, go to B, C, D, and come back at A, you're going to end up in the same location. So the entropy for such a cyclic process doesn't change. The change in entropy is 0. And as you can see, we have gotten that answer. So that's something that you just need to know when you're taking your tests. Now, if you have an irreversible process, the change in entropy doesn't have to be 0. For irreversible processes, the change in entropy is usually greater than 0. But for a cyclic process, for an ideal cyclic process, the change in entropy at best is constant. It's equal to 0. 5 kilograms of water at 80 degrees Celsius is mixed with 5 kilograms of water at 20 degrees Celsius. What is the total change in entropy? Now let's solve this using the average temperature process that we used earlier, and also using the natural log function that we came up with. But first, what is the final temperature of the mixture? Because the mass of water in the two samples are identical, the final temperature is going to be the average of these two temperatures. We have the same substance, the same quantity of water, so then therefore the change in the temperature of these two samples of water should be the same. So the average or the final temperature is going to be 50 degrees Celsius. So that the change in temperature is the same for these equal masses of water. Now let's focus on the hot water. Let's calculate the entropy change for that sample. It's going to be the heat that is released divided by T. For the hot water, the temperature changes from 80 to 50. Since the temperature is decreasing, Q has to be negative. And using the equation Q is equal to MCAT, the mass is 5. The specific heat capacity is 4184 for water. That's joules per kilogram per Celsius. And the change in temperature is negative 30, as it goes from 80 to 50 degrees Celsius. Now we know we need to use the average temperature in Kelvin. What is the average temperature? Well, if you average 80 and 50, you're going to get 65. And then convert this Celsius temperature into Kelvin. So 65 plus 273 is equal to 338 Kelvin. 5 times 4184 times negative 30 divided by 338 is equal to negative 1856.8 joules per Kelvin. So this is the change in the entropy for the hot water sample. Now what about the cold water sample? We're going to use the same equation, QC over the average temperature. So it's going to be 5 times 4184 times, this time the temperature is going from 20 to 50. So the change in temperature is positive 30 instead of negative 30. So Q is positive because heat is being absorbed. Now the average temperature, the average of 20 and 50, if you add them up, 20 plus 50 is 70, divided by 2 is 35 Celsius. Now let's convert this into a Kelvin temperature. 35 plus 273 is 308 Kelvin. So if we multiply 5, 4184, and 30, and then divide it by 308, this is going to give us positive 2037.7 joules per Kelvin. So now that we have the change in entropy for the cold water sample and for the hot water sample, the total change, is basically the sum of these two values. So if we add them together, we're going to get 180.9 joules per Kelvin. So this is our estimation. It's around 181. But now let's use the other equation and see what answer we come up with. To calculate the entropy change whenever the temperature is not constant, you can use the equation mc natural log T final divided by T initial. So let's use it for the hot temperature first. So M is 5, C is 4184, and for the hot water sample, it goes from 80 degrees Celsius to 50. But we need to convert both of these values into Kelvin. So 80 plus 273 is 353 Kelvin, and 50 plus 273 is 323 Kelvin. So T final is 323, and T initial is 353 Kelvin. So if we plug this in, we're going to get negative 1858.0 joules per Kelvin. Now let's do the same thing for the cold water sample. So it's going to be M times C times natural log. Now this time the temperature is changing from 20 to 50 degrees Celsius. Now we know the Kelvin temperature is 323 at 50 degrees Celsius. 20 plus 273 is 293 Kelvin. So now we have our initial and final temperatures in Kelvin. So the final is 323, the initial is 293. And if we plug this in, this is going to equal positive 2039.3 joules per Kelvin. So now let's add these two values to calculate the total change in entropy. So this will give you positive 181.3 joules per Kelvin. The other answer was positive 180.9. As you can see, the difference is not that great. So you can use either technique to get a good estimation of the entropy, but this answer is more accurate though. So that is it for this video. Hopefully you found it to be helpful. So do well on your next exam, and thanks for watching.